Hi, my name's Mariel. I am a postdoc at Lawrence Berkeley National Lab and also a guest researcher here at the CCA. And what I'm hoping to tell you about today is, I think, a success story of translating machine learning techniques from the world of high-energy particle physics to the domain of astrophysics. So I think it's an appropriate story for today since all of us are coming from these different domains, and I hope it can be maybe a source of inspiration that it's worth paying attention to what's going on in other fields as a way of potentially applying it to your own work. So what I'll talk about today is a problem that probably many of you in your various domains are familiar with, the problem of anomaly detection or finding rare or interesting events. I'm not sure if everyone is familiar with the concept of weakly supervised anomaly detection, but this is basically going into anomaly detection without perfect labels. So maybe you have some partial information about your data set or some noisy information, so maybe some of your labels are incorrect, for instance. So this is this domain of how do you classify objects with partial or incomplete or erroneous information. So I'll start to first take a really big step back and think about the last roughly 13 billion years of galactic evolution. So this is a simulation of what a spiral galaxy like the Milky Way could have evolved like over the course of many billions of years. And I think the takeaway from this video is that it's easy to forget that our galaxy is not static, and the evolution of our galaxy has been rather turbulent over many years. And so a lot of the stars that comprise the Milky Way came into the Milky Way from other sources. And so there are these smaller, either globular clusters or dwarf galaxies that over the course of our galaxy's evolution have been absorbed into the Milky Way. And this is super interesting. You might imagine that there's really no way of winding back the clock and actually understanding what happened, since, of course, we're only here for this fraction of a second relative to the lifetime of the Milky Way. But in fact, there are some clues to the Milky Way's history that are woven into its population of stars. And I find this interesting just from a humanity perspective of trying to understand how we got here and what our universe went through. But it's interesting for other physics reasons as well. For instance, we might be interested in mapping local substructure of dark matter in the Milky Way. And it turns out that these two properties are somewhat related. So I'll give you a picture of what we might be looking for to try to unravel these clues. So this green little blob is one of these smaller globular clusters or a dwarf galaxy that gets sucked up into the gravitational potential of the Milky Way. All this red stuff here you're seeing is dark matter, and you can see that there's this big glob of dark matter in the center of the galaxy, and there's little smaller globs that are kind of swirling around the center. And so what started as a single group, a single population of stars, over time gets stretched out and warped into this longer string of stars that circles around the center of the Milky Way. So this is what we're looking for. It's this pattern of stars called stellar streams that are remnants of external groups of stars that are still in the process of being absorbed into the galaxy. And just to give you a static picture of what these streams tend to look like, of course, this is an illustration, but we tend to have something like a progenitor. So that's the original source of the close grouping of stars. And then over time, as that grouping starts to circle the Milky Way's potential, it gets stretched out. We have this more diffuse ring of stars that stretches out in either direction. And you can see it also tends to fan out and get even more diffuse in the tails of the stream. So this has been a really rapidly developing field. So over the course of even just the past few years, we've really expanded our catalog of stellar streams that we've observed, because they're quite faint and they're hard to observe. But this gives you a sense of, when we map the sky, here's all of the stellar streams that have been identified so far. But a lot of these are going to require some cross-validation with multiple analyses to try to see which ones are really real and if any of them could be false positives. But the more the better, because the more that we can kind of map out these streams across the whole sky, we get some insight into local dark matter substructure in that area of the sky. And the reason for that is that when we look at the density of these streams along the angle of the stream, we can look and see overdensities and underdensities. And those basically can be mapped onto models of dark matter substructure. So if that stream passed through some clump of dark matter, you might imagine that would cause an underdensity in that region of the stream. And so this is one model of the density of the stream along the longer coordinate of the stream, and some potential impacts of local clumps of dark matter that stream could have passed along. So all sounds pretty cool and interesting, but the problem is that streams are very hard to identify. So this is 3 different views of one different patch of the sky. And on the left, I have position coordinates. So it's just like a circular cookie cutter piece of the sky. The plot in the middle is in velocity space, so it's looking at proper motion along each of those angular coordinates. And then the final plot is in color space. So often what I like to do with this slide is ask someone to guess where they might imagine the stream might be. This is one of the few streams that is actually visible by eye. Does anyone want to take a guess on where the stream is actually located? There. You're going to have to be more specific. I don't think we have a laser pointer, so you could point with this. Yeah?
Oh, really?
Yeah, come on, do it.
I don't know. I don't actually know. So here.
Yeah, right. There's this big blob in velocity space, right? And you might imagine all these stars came from the same source. So they probably have some collective property that's still preserved. Well, it's sadly kind of a trick question. It's really hard to find. So the scale of this is quite different. If I go back to the last plot, you can see that the y-axis, it goes up to about 1,000 counts in some of the densest bins in this histogram. But in fact, the actual stream is extremely faint. So you're right, Kays, that we're looking for this like local overdensity in velocity space. But we have this problem of being totally overwhelmed by background in most of these cases. But you can see that it has this typical stream-like, ribbon-like structure in position space, at least. So it's this tough problem. We're looking for just a fraction of a percent of stars in a given patch of the sky at a time. So the concept of the work that I'm going to be showing today is, can we repurpose a tool that was actually originally intended to discover new particles at the Large Hadron Collider in order to uncover some of these stellar streams in the Milky Way? And the way that we think about this in particle physics world is to look for bumps or local anomalies along some coordinate of interest. So in particle physics, the coordinate of interest would be the mass of the particle. And that's what you're seeing down below right here. This is like this famous plot of discovering the Higgs boson, right? Where we scan along this diphoton mass property. And then we see this bump that shows up at 125 GeV. And that corresponds to a particle of interest. So this is kind of the rough structure that we're interested in particle physics that we're using as an analogy to map on to this problem of stellar streams. And to do this, we're going to talk about finding bumps and thinking about different regions surrounding that bump. So if this bump is this orange triangle here, the signal, we can imagine drawing like a central region surrounding the signal and then a sideband region on either side of that overdensity. And then you have this nice falling background distribution that you're trying to distinguish from the signal itself. So using those concepts of sort of the central region that mostly overlaps with the signal, and then these sideband regions that they could have some signal in them, but it's going to have a smaller fraction of signal overall. So now instead of thinking about signal versus background, we're thinking about these two mixtures of signal and background that have slightly different fractions of signal and background in each one. And the concept behind this technique is super simple. It's training a classifier, but it's just using that classifier in this interesting context, where instead of feeding the classifier perfect labels of stream or not stream stars, we're just asking the classifier to distinguish between signal region, so that central region, versus sideband region. And it turns out that just learning to distinguish between mixtures of classes in an optimized setting is just as good as a classifier that has perfect access to the true labeled information. And I have some very quick math in case anyone is interested in the reasoning behind this, which is that we know that an optimal classifier, the way that a classifier learns to distinguish between different classes, it does so by learning something like the likelihood ratio. And so we can write out the likelihood ratio for a neural network that learns how to classify between these two mixtures of classes, mixture 1 and mixture 2. But we also know that those mixtures are related to fractions of the true signal and the true background. And so maybe we have some true signal in the mixture 1, F1, and then some true fraction of signal in mixture 2, F2. And so we can rewrite these two different likelihoods as a mixture of the signal and background. So then we can just plug that in to this definition of the likelihood ratio that we are learning in this overall classifier. And we can argue that this should be a monotonically increasing rescaling of the likelihood ratio as long as these fractions are distinct. And so if F1 has a larger fraction of signal than F2, then this is going to be monotonically increasing. If those fractions are flipped, then it'll learn the opposite classifier. And so we can relabel 0 to 1 and 1 to 0. But ultimately, we're defining the same classifier at the end of the day, a classifier that learns how to distinguish between mixtures, and a classifier that learns how to distinguish between signal and background. OK, so to continue this analogy, the parameter of interest, we're no longer looking in mass like we would do in particle physics. But in this case, to look for stellar streams, we look for proper motion, which is what Kays was trying to do in that earlier slide. So because these stellar streams are kinematically cold, and that means that they're very localized together in proper motion, we can try to do a scan in velocity space to try to find groups of stars that are co-moving with respect to one another. And this is what it looks like when I actually define some of these signal and sideband regions, just to prove basically that we see this really nice falling background distribution for the signal and sideband, where the signal is, of course, the darker gray, and the sideband is the lighter gray on the sides. But then when we look at the stream stars are highly localized inside of that signal region. OK, a quick aside about what data we're analyzing. The data that we look at is from the Gaia satellite. And this is what the satellite looks like. So we're specifically looking at 21 patches of the sky. So it's a subset of the sky. And they contain about 8 million stars in total. So moving on to results. So this technique, Koala, reliably identifies simulated streams super well. So first we wanted to validate this method on some simulated data, just as a proof of concept. And what we find is that it's able to identify anomalous stars extremely effectively. And that's true for just a single stream such as this one. And then also if we look at 100 streams, the vast majority of them are identified with really high purity. So that gave us some confidence that if it was able to learn in these idealized settings, it would probably do pretty well on data as well. So next up, I'll show how it does on a real stream. So in the Gaia dataset, we're going to target this one particular stream that we know exists. It's called GD1. And it happens to be especially long and narrow and dense. And so it's a good candidate for us to try to find with this technique. It also has some really interesting quirks and physical properties. So it's not just a perfect ribbon. It has gaps, and it has overdensities, and it has offshoots that go off of the main body of the stream. And all of these particular features of the stream are the ones that astronomers are interested in probing. So we're interested in trying to identify some of these physical properties, as well as just identifying where the stream is. And our technique, Koala, identifies this stream in data with really high purity. So all the rainbow stars are the ones that are identified by Koala as the most anomalous stars. And the gray are a ground truth labeling that were done sort of by hand through a series of careful cuts and cross validations. So we can see that in position space, as well as velocity space and color space, the stars identified as highly anomalous by Koala tend to overlap very, very closely with what other astronomers labeled as part of this stream. And now we can zoom in a little bit more, and we can actually look at the density of that stream along its longest coordinate. And we can see that it has a lot of these same overdensities as well as underdensities, or gaps. So those fall along similar positions as was found in this ground truth labeled set as well. It's interesting to note that there's not perfect agreement on what stars truly belong to this stream. So there have been several groups that have looked at the labeling of GD1. And this is just a sort of a rough comparison with apologies to these guys, because I had to stretch out their plot to make it line up. But you can see that there's some disagreement maybe about which of these overdensities is the most overdense, but there's some general trends that we see, which is that we tend to see these gaps at around -40 and -20 degrees, and that tends to be consistent across different metrics. And then we also see these different overdensities, although there's some variation about which one is the largest and which one is the smallest. There's pretty clear evidence for some of these offshoots as part of the stream, which is called the spur, as well as this big overdensity that's potentially the progenitor of the stream, where all of those stars originally came from, and that's called the blob. So that's what we're replicating here from other existing work to show that there are these other features perpendicular to the main body of the stream. And we also see some evidence of what's described by some authors as a cocoon of less dense stars that surround the main highly dense body of the stream. And that's what you see in these two histograms here on the right. And then probably what I'm most excited about from this work is the sense of looking at unlabeled stars that didn't belong to this ground truth labeling and getting a sense of which ones might have been accidentally omitted, or basically trying to refine our catalog of the population of these streams. And so using a classifier like this allows us to rank some of the most anomalous stars that were not originally caught in these catalogs. And so what I've plotted here are some of these highly anomalous stars that are interesting candidates for cross-validation with other catalogs to see, do they actually belong to this, the population of this stream in particular. And one of the big advantages of this technique compared to some other anomaly detection techniques that you might be interested in too, is that it's very computationally lightweight. Since we're just training these simple classifiers over and over, it's totally parallelizable. And in fact, if you wanted to recreate all of these plots that I just showed you, you could do so in about 5 or 6 hours on a single GPU. So I think this makes it a really efficient way of doing a broad scan across the sky, as well as a sort of fine-tuned refinement of these populations. And of course, if what I showed you today was a stream that we knew existed. So we had some help in defining where we should look. But as we scale this up, we won't know exactly where in the sky some undiscovered stream might lie. And so to do this, we would simply need to modify our technique a little bit such that we are searching for bumps. And so we need to define some threshold that tells us, oh, if we put our signal and sideband region here, but our stream is actually here, as we increase the harshness of our cuts on the neural network score, we don't see any obvious bump that appears in that shape. But if we are lucky and we place our signal and sideband regions over the actual stream location, then as we make harsher and harsher cuts, we'll see this bump feature start to emerge. And so then, so this is what it looks like to scale this up to a full-scale search where you don't know where to look. All right, I think that's it. Thank you.
Is there any question from Mariel? If not, then I will. Oh, can't see that.
Thanks for the cool talk. I had a question about the classifier. So could you tell us how did you decide to parameterize it, and what features did it learn to classify the interesting bands?
Yeah, this is a good question. I think I skipped this slide. So it's important that the features that you train on are uncorrelated with the signal and sideband region definition. So basically I have 6 parameters that we're looking at, right? 2 for each of these different plots. And I use one of the proper motion coordinates to define the signal and sideband regions. And then I set that aside, and I use the other 5 auxiliary variables for the training. And I think I have a plot of what they all look like. And as long as they are roughly statistically identical between the signal and the sideband region, they'll be appropriate to use. Yeah, here it is. So this is what's used for the training itself, is just these 5 other variables that weren't used to define the signal and sideband regions. And the classifier itself, it's fully connected 3-layer neural network, just to classify between signal and sideband. Yeah.
Max has a question.
This is very cool. I was wondering, the first slide you showed where you compared the koala classification to the pre-identified GD1 stars, it seemed like koala identified fewer stars towards the edges of the stream. So I was wondering if that's because at the edges it's just fading into the background, or what is the explanation for that?
Yeah, it's a great question. I have a breakdown by patch, because we sort of do it by scanning along the stream. So you can see that along the main body of the stream, it does pretty well, but there are these 4 patches that correspond to the tails of the stream where koala seems to fail. And I think it's a combination of the stream itself is naturally more diffuse towards the tails, but also some of it is that if you look at if we look in these 6 dimensions, no, the rainbow plot is better for this. This guy. Towards the tails, it's more red and more blue. And then if you look in velocity space, red and blue is also on the tails here, but here it's getting closer to 0 in proper motion, and that's where a lot of our background lives. So basically, you get swamped by background the closer you get to 0 in each proper motion coordinate.
What was the ratio of batch size to data set size for training?
Yeah, the batch size was a really interesting parameter, because we found that since there's so few stream stars in our regions, we had to increase the batch size larger than we expected in order to make sure that at least a couple of stream stars made it into the training at each point. So I think the batch size was fairly large. It was like the order of 1,000 or 10,000 compared to around 1 million stars overall. Yeah.
Any other question?
Can you go back to the last slide and say what are those harsher cuts that you mentioned? So ones that finally show the peaks.
Yeah, right. So this is looking at our test set. So we've trained the classifier, and then we evaluate the classifier on test stars, and then we take the top 50%, 10%, 1%, or 0.1% of neural network scores. So we're looking at the classifier output, and we're trying to see which ones it labels as most signal-like or most anomalous.
Okay, thank you.
I have a question. So now the way that you find outliers or anomaly, it's by scanning the space, and obviously that's not gonna work well in a higher dimensional space. Do you have any thought of going to a higher dimension so you can use more information?
Yeah, I mean, right now we're only training on 5 dimensions, so I actually think I think we could scale up to include more dimensions. For instance, there are a few parameters from the Gaia dataset that we don't consider yet, but we could in future iterations, like parallax or radial velocity. But something I mentioned in the fine print here, but I didn't say out loud, is that we can also apply some more cuts to these regions before training, and that increases the speed quite a bit, and just makes it maybe 20% lower in purity overall. So that's an option we have available to us, is that we could apply even more cuts and then do a really coarse grain scan to help increase it.